this presentation, we will talk in a little bit more detail about distributions. We will define and describe density curves and talk about the normal distribution or the bell-shaped curve. I will explain the 68, 95, 99.7 rule and ways to use the normal curve to compute probabilities and standardized scores. When describing the distribution of a variable, we should always start by creating a graphical representation because graphs help us identify the overall distribution pattern. When we look at a graph, we can immediately tell how spread a variable is, what are the values that occur most frequently, and whether or not the distribution is skewed. To obtain more precise information and to provide evidence for our conclusion, we must also provide a numerical summary of the data using the mean, the median, the range, the 5-number summary, and so on. However, the distribution of some variables in the population is so regular that it can be described by a smooth curve. Real data are represented in histograms. Curves represent a symbol or an abstract version of a distribution. Density curves are lines that show the location of the individuals along the horizontal axis, as well as within the range of possible values. So they help us investigate the distribution of a variable. But some of them also have certain properties that help us draw conclusions about the entire population. The mean, the median, and the mode can also be represented on density curves. With a symmetric or normal distribution, the mean and the median overlap. The actual recorded values may be slightly different, but they're very close. The mode will always be located at the highest point of the curve because it shows the value that occurs most frequently. The median shows the point that divides the area under the curve in half, whereas the mean, which is drawn towards the extreme observations, shows the balance point. For instance, if you want to hold a shape that describes the density curve on one of your fingers, you must place your finger under the mean to keep it balanced. When working with data collected from a sample, the mean is typically represented with the symbol x bar, and the standard deviation is represented with a lowercase s. We call these numbers statistics, and they can be computed based on what we observe in the sample. However, when working with density curves, we typically use the symbol mu for the mean and sigma for the standard deviations. These numbers are called parameters, and they describe the entire population, and they are only estimated. With very few exceptions, we don't know their real value in the population, and we just estimate these values with a certain degree of confidence based on what we observe in the sample. Density curves are used to illustrate many types of distributions. Of special interest for us is what we call the normal distribution or the bell-shaped distribution, which describes many human traits. All normal curves have symmetry. However, we must remember that not all symmetric distributions are normal. Normal distributions are typically described by reporting the mean, which shows where the center is located, and the standard deviation, which shows the spread of the curve or the distance from the mean. When the standard deviation is large, like the example on the left, the curve is wider. When the standard deviation is small, the curve is narrower, like the example on the right. One example of a variable that has a normal distribution is IQ. In the population, the IQ mean is 100 and its standard deviation, depending on the test, it's 15 or 16. If we select a random sample that is large enough, the IQ distribution of the sample will resemble the normal curve. The larger the sample, the more clear will be the pattern. For instance, the histogram in this image represents a distribution of real IQ scores as measured by the Stanford Binet Intelligence Scale. The blue bars represent the number of individuals who recorded IQ scores at a certain level. In this histogram, each bar represents an interval of 5 points. For instance, we can see that one individual has an IQ score between 55 and 60. Approximately 70 people had an IQ between 80 and 85. And the largest bar is the one for scores between 90 and 95, which includes approximately 141 or 142 individuals. I'm giving you these examples just to help you understand how the data are represented, but histograms are not meant to be read in so much detail. They're not like bar graphs. The purpose of a histogram is just to illustrate the general distribution of the data. That's why the variable is divided into intervals. If you would like more detailed information, you must look at the summary statistics. This variable has a mean of 100 and a standard deviation of 15. The curve that we draw over the histogram is the normal curve and summarizes the distribution of the recorded scores. The area under the curve represents all the individuals in the sample. If we shade only a part of the area, we're looking at a proportion of individuals who scored below a certain point. For instance, in our example, the area under the curve represents all the individuals in the sample, who in this case add up to 1,015. So this number represents 100% of the sample. The shaded area represents the individuals who had an IQ score below 90. This group consists of 256 individuals, so it is very easy to find what percentage this number represents out of the total number, which in our case is 25%. In a similar way, the normal curve is used to find proportions, but not from the sample, from the entire population. We often don't know what these values are in the entire population, but if we know that our variable has a normal distribution, we find the proportion using only the population mean and the standard deviation for that variable. However, statisticians, just to make things a little more complicated, do not use percentages for these proportions. They use numbers in decimal form. Their meaning is exactly the same, just the form is different. Therefore, instead of saying that the entire area under the curve represents 100% of the sample, statisticians say that the area under the curve is equal to 1. In this case, the shaded area will be a number smaller than 1. If we use the properties of the normal curve to find out how large the shaded area in our example is, we obtain the number 0.2546. And I will show you how to do this. It's actually very easy. Notice that the number that we obtain is almost the same as the percentage, but is represented in decimals. The numbers are not identical though, because the normal curve is just an approximation of reality, so it may differ somewhat than the numbers represented by the bars in the histogram. Normal curves help us calculate the proportions of individuals who are located within certain intervals. With normal curves, some intervals are already calculated. This is what we call the 68, 95, 99.7 rule. So if we know the population mean and standard deviation for a particular variable, we can quickly tell where the majority of the individuals are located. Obviously, most individuals are located in the highest area of the curve, which means around the mean. So if we go up one standard deviation from the mean, this interval includes 34.1% of the population. Similarly, if we go down one standard deviation from the mean, the interval includes the same percentage, 34.1. Together, these two intervals represent approximately 68% of the population, so the majority of the sample is located within one standard deviation above or below the mean. As we go further away from the mean, these proportions decrease. The next standard deviation interval includes 13.6% of the population. If we add these to 68%, we obtain a percentage of approximately 95. Therefore, we can say that 95% of the population is located within two standard deviations above or below the mean. The third standard deviation from the mean includes only 2.1% of the population. So if we add these two intervals, the 95%, we obtain 99.7. Therefore, 99.7% of the population is located within three standard deviations from the mean. Technically, the two tails of the normal curve extend to plus or minus infinite, but of course these numbers are limited when we talk about certain variables like IQ, for instance, which cannot be lower than 0. And the proportions of individuals who are located in the fourth standard deviations above or below the mean is very, very small, only approximately 0.3%. This example illustrates how to apply the 68-95-99.7 rule to the distribution of IQ scores. The population mean is 100, and the standard deviation in this example is 15. Based on the 64-95-99.7 rule, we can say that approximately 64% of the individuals in the population have an IQ between 85 and 115. Values in this interval are the most frequent. 95% of the population have an IQ between 70 and 130, and 99.7% of the population have an IQ between 55 and 145, and only approximately 0.3% of the population has IQ scores outside of this interval. The normal curve can be used to describe the distribution of many variables. So far, we've been working with the IQ distribution, but many other variables have a normal distribution in the population. For instance, we may want to compare students' scores on an ELA and a math test to determine their strengths and weaknesses. However, if scores are on different scales, comparisons are meaningless. To be able to make comparisons across subject areas, for instance, the scores must be standardized, which simply means that they're put on the same scale. There are many types of standardized scores that you may have heard of, like percentile ranks, Stanines, normal curve equivalent scores, and so on. One type of standardized scores that researchers use very frequently are z-scores. The z-scale is used with variables that have a normal distribution and has a mean of 0 and a standard deviation of 1. Z-scores can be calculated for every individual in the dataset using a very simple formula. The first step is just to compute the difference between the individual score and the population mean. The second step is to divide this difference by the standard deviation. And this is all we have to do. If the individual score is lower than the mean, then the difference will be negative, so the z-score will also be negative. This only means that the score is lower than the mean, or on the left side of the mean. Let's use again the distribution of the IQ variable to show how to transform a raw IQ score into a z-score. The image on the left shows the distribution of raw IQ scores. The image on the right shows the same IQ scores after they've been transformed into z-scores. Notice that the curve looks the same. The only difference are the values on the x-axis or horizontal axis. Instead of the mean of 100, we now have a mean of 0 and a standard deviation of 1 instead of 15. Therefore, values below the mean or on the left side of the mean are negative, and values on the right side are positive. An individual with an IQ of, say, 111 will be located in the exact same point on the curve in both cases because the score represents the same thing, only the scale is different. If we apply the formula for obtaining z-scores from raw scores, we can see that for an IQ score of 111, we first have to do 111 minus the mean, which is 100, and we obtain a difference of 11 points. Then we divide this difference by the standard deviation, which is 15, and the result is 0.73. Therefore, an IQ score of 111 corresponds to a z-score of 0.73. The next question is, how can we find out how many scores are below this point? What is the proportion of individuals who have an IQ score below 111 or below a z-score of 0.73? In other words, what is the area under the curve on the left side of this score? For every z-score, areas on the left side of the curve have already been computed for us, and they're listed in a probability table. In your textbook, they're listed in Table A at the end of the book. This table lists the first two digits of the z-score on the vertical or on different rows, and the last digit, which is the second decimal of the score, on the horizontal or on different columns. Z-scores on the negative side are listed on one page, whereas scores on the positive side are listed on the second page. For instance, for our z-score of 0.73, we first have to find the row for the value 0.7. After we find this row, we go across columns until we find the column that corresponds to the third digit. In our case, this column is 0.03, or the third column. The cell that we find at the intersection of the row 0.7 and the column 0.3 includes the area to the left of our z-score, which is 0.7673. which means that 76.73% of the population has an IQ score below or equal to 111. Or we can say that Joe's score is above or at the same level as 76.73% of the population. The normal curve can be used to compute proportions not only from one standard deviation to another, but also for specific values that we may be interested in. Let's continue working with our example. We already know that Joe's IQ score is located above or at the same level as approximately 77% of the population. We can apply the same procedure to find out the percentage of the population who scored below Matt's score, which is 85. If we transform Matt's IQ score into a z-score, we obtain the value -1 because it is exactly one standard deviation below the mean. If we look up this value in Table A, we can see that the area to the left of -1 is 0.1587, which means that approximately 16% of the population has scores below or at this level. If we want to find out the area or the interval between the two values, all we have to do is just subtract 16 from 77%, and the difference represents the percentage of individuals who scored between the two given values. In this case, the percentage is 61%. If we want to be more precise, we can use the two areas obtained from the table to do the subtraction and then transform the result into percentages. Similarly, if we want to find out the percentage of individuals who score above a certain z-score, all we have to do is subtract the percentages to the left from 100%. Or, if you want to use the area under the curve, you should just subtract the area to the left from 1, which represents the entire population. In our case, if we subtract 77% from 100%, we obtain 23%, which means that 23% of the population has IQ scores above 111. The normal distribution is also very useful for comparing variables that are measured on different scales. For instance, let's say that a graduate student has a score of 25 on a quiz and a score of 56 on the final exam. At which assessment did the student perform better? Is the score of 25 on a quiz better or worse than the 56 on the exam? The answer depends on the distribution of the two variables. The range of possible values can immediately give us an idea. For instance, if we know that the maximum possible score is 30 for the quiz and 100 for the exam, we can already guess that the student performed better on the quiz. However, if we use the normal curve, the most important information is the mean and the standard deviation. Let's say that the mean on the quiz is 20 and the standard deviation is 5. In this case, our student's z-score is exactly 1, or exactly 1 standard deviation above the mean. Similarly, the mean on the exam is 68 and the standard deviation is 12, so the student's z-score is -1, or exactly 1 standard deviation below the mean. Now we have evidence that the score on the quiz is significantly higher than the score on the exam, even though the raw score was actually smaller. We can see now that in order to compare scores that are on different scales, we have to standardize them or to put them on the same scale. In this case, the standardized scores are z-scores, but there are many other kinds of standardized scores. If we only compare raw scores, the results may be misleading. But we always have to keep in mind that these comparisons are based on the assumption that the two variables have a normal distribution in the population. In conclusion, when we try to solve a problem using the properties of the normal distribution, it is easier if we follow certain steps. The first thing that we should do is to identify the observed variable. We usually call this the variable x. In our examples, the observed variables were Joe's and Matt's IQ scores and the graduate student scores on the quiz and the exam. Then we have to clearly formulate the question that we're trying to answer. For instance, what is the proportion of individuals who have a score larger than x? It is very helpful to actually draw the normal curve and to represent the variable on the curve and to shade the area that you must identify. Then you compute the z-score for your observed variables and you use table A to find the areas under the curve you're interested in. As you have seen in this presentation, z-scores can be easily computed by hand, especially if you're looking at one or two individuals, but you can also use statistical software to obtain z-scores, especially if you want to compute them for an entire sample. In this presentation, we describe some of the properties of the normal curve, and we use these rules to find proportions and to compute z-scores. I hope that the information was clearly presented and that the examples provided were helpful.